Good morning, students. Today is October 21st, Thursday. This is our third week of the semester. And today we're going to say a couple of words about the programming of that you have to implement in chapter 2. This is a very first case that we can analyze 2 degrees of freedom for every joint. So we could analyze simple structures composed by bars in the plane. Okay, so that's that. And then we're going to start with chapter 2. Chapter 2 is very similar to the previous one. But in this case, we use line elements, but instead of in-plane or aligned forces, we apply lateral forces. And in that case, the result is going to be bending. Okay. And at the end of this chapter, be patient, we're going to combine the 2 effects. So we're going to have an element which can support in-plane force, compressive of tension, and also can sustain lateral forces or lateral effects, bending. So the 2 combined will provide us a very good tool to analyze frames in the plane. The idea is that you have a better understanding of what happens inside the program, okay? So at the end of the first part of the session, since next week we are going to have our in-person session here in Guayaquil, I would like to ask one by one in what city you are living right now. Okay, because I would like to set something up. Okay. Okay, so that's the agenda here. So can you see my word projection? Anybody? Can you see my word? Yes? Okay, thank you. So we were in green, we were discussing what data do we need to perform these calculations? And we said, okay, we need the number of joints. In this case, for example, you need 4, okay? You need the position of the joints. For every joint, you need the X and Y position. You need the number of elements, okay? You need the connectivity table. So for each element, you need to tell the program your joint 1 and your joint 2, okay? Somehow. Then we need to specify the number of external forces, okay? In some joints, you have an external force. If you say that I don't have external force, that means that external force in that joint is 0. That's that, okay? The number of that, for each one of them, its value. Now, here we have to complement this, okay? Because when we say the external forces, we have to differentiate between force in X and force in Y, okay? So let me complement this with the same color, if I can find somewhere. See, here I'm going to complement this parentheses. Remember, there could be 2 components. Okay, in X and in Y directions. So we have to be careful with that. Then this is extremely important. We need the boundary conditions, or in this case, remember that the only conditions that we input are geometric boundary conditions, okay? So we need to specify how many supports do we have, and for each of them, we need to specify the direction, okay? For example, in this case, you don't have the possibility of moving in the X direction, okay? So you have to say, okay, this is one point, but the direction is X, okay? You could have something like this, for example, like this. And in this case, in this joint cannot move neither in X, neither in Y. So you need to specify both, okay? And finally, we have to complement this in the same way as we did before, okay? Since not only we need to specify the direction, but also the value, okay? So let me complement this in saying that for geometric boundary conditions, okay, we need to specify the value of the displacement of that joint. Okay, for example, right now with engineering SAC, we are working with, it's a bit more complex than we are doing here, but in general, for example, let's suppose that we want to analyze a plate, okay, like this, and we are including something like this, just like that. And this is guided like that, okay? And what we're specifying is that this edge, the upper edge, moves vertically a certain amount, okay? So in this case, the condition is that, okay, this edge moves downward, for example, 1 millimeter. But this is a known value, and the known value is not zero. It's different than zero. So in this case, for example, we could specify this. This could be, for example, the displacement of this edge in the Y direction. Okay? So it's not zero in this case, it's different than zero, but it's a value that we know. Okay? And after you do that, remember that we could specify that, or we could, when we solve the system of equations, okay, we have to specify that on the right-hand side of the equations. In the example that we presented in class, we explained that. Okay. Just, I don't know, is there any questions about this, this implementation so far, people? Anybody? So far, is there any problem that you're having with this assignment? Anybody? No? For example, this is the way I tend to do. Remember that I don't program with Python. I program with another language, programming language. But for example, let's suppose I have, this is the system, okay? And let's suppose I have two joints here, and these two joints form one element, okay? For example, let's suppose that this joint is joint 12, And this joint here is joint 9. And this is element 5. Okay, so all of this information has to be read from the data file. This is an external file where you have all of this information. And for example, what I do, be patient, be patient. What I do is I define an array. I think you call this in a different way in Python, but it's like a matrix with 2 subindices. That's an array. You could have arrays of 1, 2, 3, or several degrees of freedom. In this case, for example, for this, I use an array of 2 dimensions. For the first, let me save just in case. Jesus Christ. Doesn't want to work today. Damn it. In the meantime, as we expect this, Alarcón is here. Is Alarcón here?
Yes, doctor.
Do you live in Guayaquil or outside?
I am living in Guayaquil.
Okay, so there is no problem with you. Okay, I just wanted to keep track of that. Okay, now let's see. Let me save this. Okay, now let me go on with this. Okay, for example, in this case, okay, we were discussing this implementation. Okay, now what I do, see, I defines an array, to the array. For example, with the joints which define every element. Okay, for example, I call this array, for example, ij. So this is the array ij, and this array gives me the number of the joints of every element. Okay, so what I said is that I use 2 subindices. And for example, the first subindex, I use it to define or to specify the number of the element. Okay? And here, since for every element I have 2 joints, I have to specify the number of the joint of the element. In this case, since we are using line elements, we have either 1 or 2. Okay, for example, in this case, let me change color to help you try to follow my explanation. Let me change color. Let's use this one here. For example, let's suppose that I define this 5th element, this 5th element, and this is the direction, the local x direction of this element. Okay, shoot. Okay, so this is the local y direction. So joint 9 is the first joint of this 5th element, and joint 12 is the second joint of the 5th element. So in our case, we can say that the number of the joints, this is the example, okay? The number of the element, let me go back, is the fifth element, okay? So here, I'm talking about the fifth element. And the first joint is the joint, this one here, which is joint 9. Okay, this is equal to 9. So what I do is when I read the information, okay, for every element, I have to read this information. And also, I have to read for the same element, okay, for the second joint, I have to read the other, which is 12. Okay? So in this way, I know that the first joint of the fifth element is joint number 9. The second joint of the fifth element is joint 12. With this information, I can go on and calculate all of these properties. Continue with this example, right? Once we know the two joints which define an element, okay, we may calculate length and cosine and sine of the local reference system. Now, that's just pure geometry. Okay, for example, in the case that we were explaining, see, I have this and that. Okay, I have for this joint, I think it was joint 9. Okay, let's suppose this is joint 9 and this is joint 12. Okay, since this is X local, okay, this is Y local, okay, this is going to be theta for this element. But in this case, for example, the length, this is the fifth element, is going to be what? The square root of the second joint is going to be x12 minus x9 squared plus y12 minus y9 squared. And the cosine is going to be delta x, so it's going to be x12 minus x9 divided by the length of the fifth element. And the sine is going to be delta y divided by length. So, see, remember, I don't write cosine of theta, I just write a big C or big S. Okay, and this is what we mean by sine theta of the fifth element. But I don't want to write all of that. So it's equal to delta y, so it's going to be y12 minus y9 divided by the length of the fifth element. People, any questions? People?
No.
Okay, nobody. Okay, fine. And similarly, for the forces, okay, similarly, for the external forces, and for the displacement for the specified displacement. In this case, see, let's suppose that we have a system, and let's suppose that I have a joint, or see, it's composed by several elements, And now let's suppose I have a force like this one here. Okay, so that's the force, for example. Let's suppose that this is the sixth. But this is a vector. So you need to specify the number of the joint, the direction. Of course, the direction is either 1 or 2. So 1 means x direction and 2 means y direction. Okay? And also the value. Okay, so in this case, for example, I would say that the force, apply it in the, well, we need to specify the number of the external forces. Now, for example, this is the number of the external forces. Okay, then we specify the joint. Okay, so this is the joint number, and this is the direction. Okay, so with this, we could go on and specify the position. Question for you. Let's consider that we are, oh shoot, not responding again. Mr. Arias, do you live in Guayaquil?
Yes, doctor. I live in Guayaquil.
Mr. Barba?
No, doctor. I live in Puerto López, Paz, Puerto López.
So you will be traveling next week?
Yes, of course.
Okay, good. Okay, let me go on with this because already we are back. Oh no, yeah, we're back. Okay, so we need to save all of this information in this array in order to keep going in calculations, complete the calculations. Okay, for example, let's suppose that this is a question for you. Please, I'm going to call somebody to answer, so just hold your answer, okay, until if I call you. Okay, for example, we had this exercise, this example from before, okay? So let's suppose I have this case, okay? We have the fifth element, and the fifth element is connecting joint 9 and joint 12, okay? Please keep that in your mind. So 9 and 12. Okay, so here. So let's suppose that, so I said the example is that we are analyzing the element 5, which is connecting joint 9 and joint 12. Okay, so let's suppose that we calculate the stiffness matrix of this element, a fifth element, okay? Remember, this is a 4x4 matrix, okay? Question for you. Okay, so I'm going to include this into here, okay? Okay, so for each one of these lines or rows of this matrix, I'm assuring the equilibrium of the joint, of each one of the joints in the X and also in the Y direction. Question for you. The first, let me change color just to help you. The first row the first row of this equation, of this matrix, of this element matrix, the first one here, in what position, this is the big K, the global stiffness matrix, in what position are going to be included? Please take a couple of minutes to try to determine the answer, and then I'm going to call somebody to answer that. Okay? So this is the element 5, number 5, which is connecting joint 9 with joint 12. Okay? The first row of this matrix, this is a 4 by 4 matrix. I want you to tell me in what row are you going to include this information in here in the global. Let's go to the end of the list here. Mr. Guerrero, could you answer that? See, the first row of this, in what row is going to be included in the global stiffness matrix? This is the big K. This is our big K. This is little k, this is big K. Mr. Guerrero, did you answer? Did you understand my question?
Good morning, doctor. Where I put the information.
Yeah, you have to tell me the number of the row. See, each one of these is a row. We have many rows. The problem is that this, the first one, I want to know, see, this is going to be included in one of these. If this is the 9th element, the 9th joint, I want to know in what position is this going to be included. Okay, Miss Freire, can you answer that? Miss Freire?
Good morning, doctor.
Yes, tell me. See, joint one, how many rows do you use for joint one?
Four.
No. Every joint has 2 degrees of freedom in X and in Y. So for joint one, I have F1X, F1Y, etc. Then I go for joint 2, 3, and 4. So Mr. Ordóñez, tell me, in what row are you going to include the first row of this local stiffness, and I'm sorry, the element stiffness matrix? Mr. Ordóñez?
The first two are in the row 17 and 18. And the two end, for example, is that the joint.
How did you get it?
I did a formula for that.
What's the formula, please? Could you share with us the formula?
The joint minus 1 times 2. That is the first row. The second is plus 1.
1, yes. So this is the number of the joint minus 1 times 2. 2 because you have 2 degrees of freedom for every joint. And the next one, of course, is that number plus 2. So it's this plus 1 more. Thank you, Mr. Ordóñez. And again, this row here will go with this row here. And the next one goes like this. There. So I have these 4 elements. These go for these 4 elements. So this goes here. Thank you, Mr. Ordóñez. Good. We can go on. For example, let's see. Okay, so that comes a very difficult thing. So this part here, I also have 4 elements. Question, in what column? Oh, Jesus Christ. Believe it or not, this is a vertical line. What column is this one here, Ordóñez?
This is the column 22.
So it's going to be, give me your formula, please.
That is 12 minus 1 times 2 plus 1. Sorry, that is without plus 1.
Yeah. And the next one, because I have 2 here, is going to be plus 2. There. So I have 4 elements here in blue, and these 4 elements are this one here. Okay? And you can see that all the information that we have read is being employed, because we know that for the 5th element, the first join is join 9, is something that we already read. The second join is join 12, and all of this goes here. Okay? So with the number of the joins, as Mr. Ordóñez explained, -1 times 2 plus 1 or plus 2, that will specify the number of the row where you have to input the information. So for example, let me go back a little bit. Okay, if you say that the force that you are applying is in the x direction, and in that case, that will go in this line. And if the force is in the y direction, then you go in here. Okay, so you know the joint, you know the direction, so you know where to put this force. Okay, similarly, very similarly with the case of the displacement. Okay, again, it's not responding. So since when the system doesn't respond, okay, I'm going to take advantage of that and keep asking. Mr. Vallas, you are in Ambato, right? Mr.
Yes,
Vallas,
yes,
you're going to be traveling next week. Mr. Cano, where are you? Mr. Cano, could you answer, please? No, it's not here. No. Mr. Carrillo, you are in Riobamba, right? Mr. Carrillo? Mr. Carrillo, you see, there is some people who I just turn on the camera and that's all. Mr. Carrion, where are you? Mr. Carrion?
Good morning, doctor. I'm now in Guayaquil.
Okay, good. Mr. Cueva, you are in Guayaquil. Are you in Guayaquil, Mr. Cueva? Mr. Cueva? No? Okay, let's continue with the explanation since already I got the control back here. Okay, so the external force and the displacements are very similar. Okay, so you need to specify the joint, the direction, so either X or Y, and then the value. Okay, yes, if you have a simple support, of course, the displacement is going to be 0. But as I said before, you could have cases where you have the displacement, it's an amount which is not 0. So you have to specify that value. Okay, for example, this is what we are doing with Engineer Isaac. And in this case, we specify this value to be, for example, 3 millimeters. So it goes down that slowly, okay, buckle, and it keeps going. But we specify how much this value is. And the result of that is that we know that value and we're going to calculate the force that we need to apply on this end in order to get that displacement. Okay, so if you have a support, which doesn't move, of course, the value is going to be 0. And of course, the force that you need to specify there is going to be the reaction.
I have a question.
Yeah, go on, please.
In that case, in the displacement, we know that value because we did the experiment, but in the case of the sample, for example, in the force applied, we don't know the displacement.
Yeah, there are two cases. There are two cases. It's something quite that we mentioned in ship structures. In one point, this is something that we insisted in ship structures. In one point, okay, or in this case, in one of the ends, you either specify the displacement or the force. The other boundary condition has to be either the rotation or the moment. You cannot specify together the displacement and the force. Same thing here. You say, for example, that the upper edge moves downward, okay, but you do not know the force. You calculate the force as a required force later on. Let me go back. So what I'm saying is this. Okay. I have big, these are the displacement, and these are the external forces applied on the joints. So let me put it, this is big K, okay? So in the same way as in the example that I presented last session, let me say that this is the 1y. Let me put this element, this value, big D, that means that we know that value. And in this case, immediately, this force is unknown. So in this case, no, that means that we do not know this value, we do not know this value, we know this value, but this is unknown. So we know this value, so this is F, big F, 1x, big S, 1y, etc. So we see in this case that we have one unknown, two unknown, and three unknowns. And we have three equations. Okay, so you either know this and this is unknown, or the other way. You do not know this and you know this one. But for every equation, you either know this or that. Did I answer your concern? I don't know, the person who was asking me.
Yes, I am going.
Okay.
A little bit about that matrix. For example,
Yeah.
the D1 in the assignment, we don't know the first 2x.
Let me go. Okay. Are we clear with these people? Is there any questions about this process? And remember, okay, remember that we have said is that you don't have to do it, but believe me, please believe me. I have some experience on this. I can assure you that you can take from this system, you can take the first subsystem, but the problem is that you have to rearrange the number of equations, the number of unknowns, the number of independent terms. It is very complex. It's much easier in this case that we take this term here, see, in the same line that we know this value, and we put here a big number. And this value here that we do not know yet, we put it big, the same big number multiplied by d2x. Remember that when we put big D, that means that we know this value. Okay? If this is a very large number, okay, the solution of this equation since this is very large, larger than any one of these, the solution will be simply this times this equal to the same big multiplied by D2, because the other terms are very small. And of course, the solution is that D2x is going to be the required value. Okay, so it's much simpler, but you can try to extract the subsystem from here and then solve it. But believe me, it's very complex when you try to set up the new numbering of equations, of unknowns and independent terms. Okay, let me go back now. Then I have to close this. And I'm going to open the homework if I can find it. Here it is. People, can you see the homework? Okay, good. Why don't you people turn on your cameras, please? I need to talk to somebody. Thank you. Next week, I'm going to be extremely happy when I finally know you. I know that you don't want to know me, but I would like to know you, who you are. And say, nice to meet you. Okay, Ordóñez, you were telling me something. What?
That is wrong about the for example, we don't know the force F, right?
Exactly.
And that joint also we don't know the displacement.
Yep.
Yeah, but so in that case, in the system, we cannot put the two variables, right?
Okay. Okay. Let me go back and let's read the question. Okay. So in this case, it says you need to determine the maximum load that might be applied in the structure so that the maximum stress is below the yield point with a certain safety factor. Okay. Any suggestions to solve this problem? Because we don't know F and we don't know D. Any suggestions to solve this problem? You want to know what's the maximum force that you can apply here so that nobody has a stress larger than 235 divided by 125. Any suggestion, people? How can we do it?
We can apply a force minus the yield point to see and then see the value of the displacement and compare.
Yes. And how are you going to determine the maximum force? So I mean, I'm just trying to make you think, that's all. See, I can apply any force, right? 1, 200, 1,000, 1 million newtons. And then what? Mr. Ordóñez, go on.
And solve the system of the equation, right?
Okay.
And then we will have the displacements of that point.
Yeah.
So I don't know, I can compare that value with the
but the problem with this, see, you are correct. The problem is that I am not saying anything about the displacement. In this case, the mode of failure that we are considering is the strength. So you have to think about how to calculate the stresses. And the stress, the maximum stress in any point has to be below the yield point.
Okay, that is compared with
What are you going to compare?
With the stress.
No, but what are you going to compare?
Oh, the The stress that we
Exactly. In what element? In what element?
element, the joint one or the joint of the force.
In what, people, where you, in what element would you what element would you consider?
Where is maximum force?
Exactly. Not the maximum force, the maximum value of stress. Yes. See, what I would do is I apply a force, any force that you want. Then I get the maximum stress. Let's suppose that I apply a force of 1 ton. And let's suppose that the maximum stress is 100 newtons per millimeter squared. See, I apply a force of 2 tons, and I get 100 newtons per millimeter squared. What's the maximum force that you can apply? How would you do it? See, let me try to write it here. See, I apply a force here of 2 tons. And let's suppose, I don't know where, but let's suppose that here, sigma, in this element that I don't know which one it is going to be, let's suppose it's 100 newtons per millimeter squared. Question for you. What is the maximum force? Because that's what we are looking for. What's the maximum force that you can apply in this situation? Now, question for you. What would happen if instead of 2 tons, I would apply 1 ton? How much would be this one here? If I apply, instead of 2, I apply only 1. How much is going to be this value here? You have something, Miss Lopez, do you have the answer? If I, instead of 2, I apply 1, how much is going to be this stress? Ms. Lopez?
Area for...
No. Come on, people. This is a linear problem.
It can be the half of...
How did you get it? Why you...
Per...
Exactly. So, how did you get it?
Because it's a linear problem, we can...
Exactly. That's all. And we insisted, this is a linear analysis. Okay, if you do a master's degree and you want to work with structures, yes, I will ask you to go non-linear. This is linear. This is undergraduate. Question, now, if I need to reach, let's suppose that I need to reach this to 235. How much is going to be this? Peralta, how much is going to be?
I think that we need to iterate and...
No.
4.7.
How do you get it?
With...
That's correct.
I don't know how to say.
Yeah, see, this is what you're doing is this. See, you're saying, remember, this is what we did in high school. So if I apply 2 tons, sigma is 100 newtons per millimeter squared. How much is the force if I want this to be 235? So the max force, let's call it star, it has to be 2 times 235 divided by 100. And that's what you get, 4.7. And we can do this because this is a linear analysis. Okay? For example, when you did you started to study stability of the ship. Okay, you said GC is equal to GM times theta. Okay, but that means that if you go like this, 90 degrees, the GC is going to be GM times theta? No, because that's valid only in a certain range, in the linear range. In this case, we are not saying anything about the limits. So that's why we can apply directly linearity. Okay, let's take a break, and when we return, let's see if there is any other questions about this. In the meantime, let me keep, this is our break. If you need to go to the bathroom or whatever, do it now, but I need to keep asking people. Mr. Cueva is not here. Mr. Cumbe, you're in Guayaquil, Ms. Cumbe? Yes.
Yes, doctor.
Okay, thank you. Mr. Diaz Tucta, where are you?
I am in Guayaquil.
Okay, well, good. Mr. Diaz Bisuete?
I am in Guayaquil, doctor.
Okay. Miss Freire?
Guayaquil, doctor.
Mr. Galarza?
In Guayaquil, doctor.
Mr. Guerrero?
I'm in La Troncal, doctor.
But the next week, can you travel in the morning and go back in the afternoon?
Yes, doctor.
Okay. Miss Gutenberg, you are in where?
I'm in Ibarra.
Wow, nice. How is the weather there?
The weather?
Yes.
I'm sorry, I don't understand.
The weather. I mean, this is very cold, it's rainy, it's sunny.
It's very cool. Very cool.
We should visit. We should visit.
Yes.
Mr. Wacon? Mr. Wacon?
No, I live in Machala.
So you'll be traveling next week?
Yes, doctor.
So you have to stay here, right? 3 days. Okay, Mr. Iñiguez. Mr. Iñiguez.
Good morning, doctor. I am in Guayaquil.
Okay. Mr. Jimenez.
I'm in Guayaquil, doctor.
Okay, good. Miss Larrea, you are in Quito, right?
Yes, doctor. Good morning.
Good morning. So you will be traveling.
Yes.
You like it? How many hours do you spend in traveling? How many hours?
8 hours.
Ah, wow.
Yes.
Okay, Mr. León Tumbaco. León Tumbaco? No. Miss Lopez?
I live in Ibarra.
Okay, so you will be, yeah. I'm sorry, I forgot for a second. So you will be traveling next week, right?
Yes.
How many hours do you have to travel?
5 hours.
That's not much. Miss Matias? Miss Matias?
Yes, I live in Salinas.
Nice. How is the weather in Salinas? How is the water? Is it very nice to get into the water, or it's very cold yet?
Very cold.
Oh, shoot. Mr. Matute? Mr. Matute? Mr. Nevares? You live in Guayaquil, right? Mr. Nevares?
Yes, Guayaquil.
Okay, good. Mr. Ordóñez?
I'm waiting.
Okay. Mr. Ortega? Where are
Yeah,
you,
in
Mr.?
Guayaquil. Guayaquil.
When did you return?
Like 4 months ago.
Oh, shoot.
It's too cold for me
Prueba.
You should try Michigan. That's really cold. Mr. Peralta, are you in Guayaquil, right? Mr.
Good
Peralta?
morning, doctor. Yes, I'm in Guayaquil.
Good. Miss Pincay?
I'm in Guayaquil.
But are you originally from Guayaquil, Miss Pincay?
Yes, I am from Guayaquil.
Okay, good. No, then I'm confused. I'm sorry. Mr. Ramon?
Good morning, doctor. I live in Machala.
So you will be traveling next week?
Yes, I tried to find Airbnb for I stay 3 days.
Okay, okay. Mr. Ruiz, Ronnie Ruiz? Ronnie Ruiz, no? Miss Sayo? Miss
Good morning.
Sayo? Good morning.
Right now I'm in Guayaquil,
But you originally from where?
from Machala.
Okay.
I traveled in this week.
But you're living right now, so you don't have to travel next week.
No, I am with my family.
Okay. Mr. Sanchez?
Good morning, doctor. I'm in Puerto Viejo.
Wow. So you have to travel.
Yes, doctor.
How many hours do you have to travel?
4 hours.
Did you have the problem because this bridge fell down? Is that where you live?
I have to pass this road,
Okay.
but I think that they built another road side by that bridge. I think.
Okay. 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 So there's no problem. Good. Thank you. Miss Vega? Miss Vega?
I am Leona.
Oh, okay. Yeah. So you will be traveling?
Yes,
How many hours do you spend in traveling?
4 hours.
Oh, it's not much. It's not so bad. Miss Vera? Miss Vera?
Morning, doctor.
Good morning.
Guayaquil.
Okay, good. Mr. Zambrano?
Good morning, Dr. Yes, I'm in Guayaquil.
Okay. But you were outside the country, right?
Yeah, last year.
Where were you?
I was at Wisconsin Dells.
Okay. Madison, Wisconsin. Now,
No,
what's a
Wisconsin Dells, Wisconsin.
That was a
Madison
nice university. Zamora, Mr. Zamora.
I'm living in Milagro.
So you next week you will be coming and going. So you come in the morning and come back to your home in the afternoon. Is that correct?
Yes, doctor. Of course.
Okay, okay, okay. So I'm asking because I would like to offer you, those of you who come from outside, I would like to offer you something for lunch. Okay, so I'll talk to my wife and we decided we can help you with that. So those of you who come from outside, I will provide you with lunch on Wednesday and Thursday. Okay, so we can sit. If the other students bring lunch, we can sit and chat and know each other, right? But yeah, those of you who come from outside, I will offer you a lunch, okay? Okay, let's take a break now. Let me save this. Let's take a break.